All right, folks. Welcome back to another class. I'm just noticing my mic here is a little low on battery, so if I cut out audio-wise for online people, pop something in the chat, although I'll be keeping an eye on it myself as well. We'll see how long we can go. It's been charging for a little bit, so it's got some juice. We're going to start a new unit today. I wonder if I can actually, like, it's funny, I could plug it in and charge it while I'm talking, which kind of defeats the purpose of a wireless mic. But hey. So we are going to start a new unit today. And I recognize that our previous unit, we left a couple of slides right at the very end that we didn't cover. And I decided just to start fresh today, because the remaining slides were just a couple of slides on sort of recent political, and by say recent, over the last 20 years, notable events that happened in sort of the political negotiations and whatnot around legislation regarding greenhouse gases and climate change. So I think what I'm going to decide to do is, like, you can read that yourself, go through the slides. There's one or two questions maybe at max, and I'm confident that we can start something new today. That means I'm setting the due date for the unit assignment for the global warming one to be 1 week from today. And that's already been set. So just be aware of that new due date coming up, and we're going to start the new unit today. And the next assignment is actually live. We probably won't finish this unit in a single class, but we might finish it Thursday. We'll have to see. This one, after this current unit, we have a few more to go. And our next one is going to be on cannabis chemistry. After that one, we have a couple more, depending on how many classes we have till the end of the semester. There's one on plastics, specifically plastics in the environment and different types and stuff. There's one on nutrition. There's one on pesticides, and we'll see where we get. I'm not in a big hurry, but it'd be nice to cover more material. It's all interesting stuff. So today we're going to start off by talking about a substance called dihydrogen monoxide. And there's a website, dhmo.org, with facts about this substance, dihydrogen monoxide. It tells us that this stuff is an industrial solvent. It's a liquid. It's a picture of it right here. It's a widely used fire retardant, put out fires. It's added to swimming pools to maintain chemical balance. It's a byproduct of combustion in automobile engines. And it's a coolant used in nuclear reactors. So many, many uses for this substance. Apparently, there's about 400 deaths a year in Canada due to accidental inhalation of this substance. Other things, contributes to soil erosion. Vapor is actually a greenhouse gas. Its use has increased in North America annually every year, starting back in the 70s. It's a component of acid rain, and it's found in rare precancerous growths. What about action, though, on this particular substance? Well, in 1994, a researcher named Nathan Zoner found that 90% of people he polled in the US supported an outright ban of this chemical, that it shouldn't be used at all in the United States. In 1998, the Australian Parliament, on April 1st, introduced a bill to ban the substance in that country, which was unsuccessful. 2010, time has passed since 2010. We're now in 2022. And none of the developed nations in the world have passed any meaningful legislation to limit the usage of this substance. Why do you think that is? Yeah. It's just water. Yeah. DHMO, dihydrogen monoxide. 2 hydrogens, 1 oxygen is water. And what about all that stuff we said? Well, it's an industrial solvent. Yeah. It's used to put out fires. Yeah. It's added to swimming pools. Sure is. It is the product of combustion in automobile engines, that and CO2. And it's used in to cool nuclear reactors. This is drowning, by the way. Accidental inhalation would be drowning, deaths. Soil erosion, definitely. Greenhouse gas, it is. Use is increased. It's a component of acid rain. It's the rain part. And it is found in rare precancerous growths. It's found in all biological tissues, I believe. So none of these were lies. All of these were facts that were put together by this researcher, Nathan Zoner, who was a high school student doing a science project on, you know, how easy it could be to sway the public into accepting an opinion given a couple of facts. And so basically what he did is he went to a mall, he set up a little booth, he made a poster, and had these facts on it, and he engaged people as they were shopping and was trying to see if he could get them to sign his petition. And what he found is that 90% of the people he talked to were eager to sign and have this thing banned. So it was really the purpose of his project was just to really show that people without a lot of evidence or research can be swayed to somebody else's opinion if it's presented in a persuasive way. April 1st, this was an April Fool's joke. See the date there. And obviously, there's a reason why nobody has limited this, of course. We need water. So this whole unit is going to be on water. And in particular, we're going to focus on water that we drink. And water, clean drinking water is an extremely important part of public health. And we're going to talk about what happens, how the water that we drink gets to us, and different things that could be in our water, and what we need to worry about and not worry about. So first of all, the Earth is covered in water. And if you were to take all of the water on the Earth, out of all the oceans, rivers, lakes, and everything, and make one big ball of water, that would be about the size of the ball of water relative to the size of the planet. I'm going to make these slides a bit bigger. You can see it. That's all the water in the world sort of in one ball. That's compared to all the gas in the atmosphere in one ball. So, you know, we got a lot of water for sure, although compared to the size of the planet, maybe it doesn't seem that impressive. So of the water on the Earth, almost all of it is in the oceans. 97.4% of the water on Earth is in the oceans, which, you know, is great for the fish and everything, but it's not water we can drink. Can't drink ocean water because of the salt. And we can drink fresh water, which makes up like 2.5% of the water on the Earth. Of all of the fresh water on the Earth, most of that is inaccessible to us because it's in ice caps or glaciers, which are typically in remote, unpopulated areas. And also a lot of it is in groundwater, which actually is accessible to us. That's what we get when we drill underground and pull water up from below. Lakes, rivers, atmospheric moisture, moisture that's like in the soil if the soil's damp, all of that contributes only 0.014% of all of the water on Earth. So the water that we see, the fresh water that we like see and interact with, the rain, you know, the rivers and lakes, tiny, tiny fraction of the water that we have on Earth. So of the fresh water, about 70% of it is in ice caps and glaciers, which is a huge fraction. We can't really use that, right? Except I think there's a kind of vodka that you can buy that's made in Newfoundland where they take not glaciers, but icebergs. They tow them in from the ocean and they haul them up on land somehow, and they use the meltwater from the icebergs to make their vodka. Anyone hear that before? No? It's a thing. I forget what it's called. But anyway, that's about 70% of water. And when you look at that, that's a lot of water compared to like the size of a person you can see there. About almost all of the remaining 30% is in groundwater underground. And this is what we use when we, you know, drill a well or dig a well. You are accessing the groundwater and you can pull this water up. So there's huge reservoirs of fresh water available to us underground. And, you know, that's great if you're on a well system. And a lot of like tap water actually comes ultimately from wells. Like I live in Port Williams, and I'm on village water, which means I plug into a pipe and then I just get water from the village. But all of that water actually comes from a well that is pumped into a water tower and cleaned up and sent to my house. If you think about what people use water for, we think about water, it's nice to drink and so on, but actually very little of the water that we end up using is for drinking, probably less than 1%. Globally, about 70% of our fresh water is used for irrigation, typically crops, right? 22% is used by industry for various industrial processes like cooling or things like that. And only about 8% of our freshwater use is for people like you and I, and domestic use means basically in our homes. So we're narrowing down all the water in the world, fresh water that we can access. Of that fresh water that we can access, the stuff that's actually used in homes is getting smaller and smaller and smaller. Of that fraction that we use in our homes, about half almost, or even more actually, like 70%, is used outdoors, usually for people watering their lawns. Probably here in Nova Scotia, it's probably less than that number. Sophie tells me it's iceberg vodka. Thanks, Sophie. Or Sophia. Yeah. My eyes are, I got it now. Thank you, Sophia. So 70% is used outdoors. As I said, probably less than that in Nova Scotia because we got a lot of rain and not long, dry summers. So my lawn stays green all year, only because there's not much grass in my lawn. It's biodiverse. There's a lot of weeds and stuff in there. Then you see all the different things, flushing the toilet, laundry, showering, all these different things. A lot of it is actually lost to leaks, leaky taps and things like that. So probably way less than 1% that we actually consume in our food and in our, like when we drink. All right, question 1. We do have this new unit quiz live. And the question says, how much of the fresh water on Earth can be found in lakes or rivers? And 80%, greater than 80%, majority is found. About half, about 25%, about 1%. The correct answer is about 1%. Very, very small fraction. Which is pretty nuts when you actually see like a huge body of water like Lake Ontario or something like that. And you realize, this is just like literally a drop in the bucket when you think about how much water there is on the planet. Structure of water. We're going to get into a bit more chemistry here. Who was it that figured out the structure, not the structure, but the formula for water as being H2O? Anyone remember? It was a British guy, and he used a battery to figure it out. No, it wasn't Faraday. It's Humphrey Davy. And that was before the strike. He made this big battery, and he stuck the 2 electrodes in water, noticed gases bubbling off the electrodes, and he collected the gases and found they came off in a 2-to-1 ratio. He realized one of those was oxygen. Oxygen had been made before in a pure form by a different scientist named Joseph Priestley. And the other one he knew was hydrogen. He could burn them 2 together and get water back out. So he figured out the composition of water as being H2O. Since then, we've learned a lot more about the structure of water. It's a molecule with 1 oxygen, 2 hydrogens in each molecule. There's a covalent bond, a single covalent bond holding together each hydrogen to the oxygen. And it forms this bent structure with a bond angle of around 104.5 degrees. Okay, so we know quite well what water looks like. There's various representations. You see it sometimes like this, or this, or this, or this, or this. So they're all good representations of water. Remember in the last unit we talked about electronegativity? Electronegativity was when you have a bond that's a covalent bond. And it talks about how one of the elements in that bond can pull the bonding electron pair closer to itself, giving itself a negative charge and giving whatever it's bonded to a partial negative charge, or positive charge. And it makes a polar bond. It's sort of, you get this imbalance of charge. And what happens then is you can have a molecule that has like a positive end and a negative end. And when that happens, the positive end of one molecule will attract a negative end of another molecule, and this can cause a whole collection of molecules to want to stick together. So water has this. It has a very electronegative oxygen atom and a not very electronegative hydrogen atom. So you get this very polar bond, with the oxygen being where the negative charge gets concentrated, and the hydrogens where positive charge get concentrated. So that makes water a very polar substance. Call it a polar liquid. Okay? And that has a huge amount of, a lot of the properties of water are a direct result of this, as we'll see. So yeah, water, this is some ways of representing it. It's got that delta minus means partially negative. It's not a full -1, but it's like somewhere between 0 and -1. And then the hydrogens get these like partial positives. So the negative end of water, which is this end, will attract the positive end of another water molecule. They'll stick together. We have a name for this, by the way, this sticking together of molecules like water. We call it hydrogen bonding. Anytime you have a molecule that has an OH bond or an NH bond, they are very polar bonds, and they stick to similar molecules that also have nitrogens and hydrogens to them. So water molecules stick together well, which is actually interesting because water molecules, when they stick together, they don't want to separate and become gases. Because if you turn them into a gas, all these molecules are separated and you've broken all of these forces of attraction, which we call hydrogen bonds. So water likes to be a liquid, and we know water at room temperature is a liquid when almost all the other small molecules are gases at that temperature, like CO2 or N2 or O2 or all the noble gases or methane, CH4, all the CFCs are gases at room temperature, which are chlorofluorocarbons. So like water's unique. It's a small molecule that's a liquid at room temperature when most gases are small molecules. So this hydrogen bonding extends in a liquid sample. It extends in all three directions and holds all these water molecules together as one collective, I guess, drop of water if it's a small little thing. If you took water and you sprayed it up in the air, it's going to come down as drops, and each droplet forms this like sphere where all these water molecules hug together and try to be as close to each other as possible. Water molecules don't actually want to be on the surface of the drop, if you have a drop of water, because water molecules are most stable when they're surrounded by other waters. Because if they're on the edge, they're touching air, and if they're touching air, that means there's potential areas that could have stuck to something else, but there's nothing there to stick to. And so that's why water, when you make a droplet, they tend to form balls, because a sphere is the shape that has the minimum possible surface area for that given volume of substance. So by forming a ball, it minimizes the number of water molecules that have to be on the surface, and the maximum number of water molecules are completely surrounded by other waters, which is their ideal way to be. It reminds me a little bit of bees. The insect makes honey. What they do in the winter to stay warm is they form like a ball of bees, and they're all kind of like vibrating and moving, and they have the queen in the center. And the queen in the center basically stays warm because of all the other bees that are surrounding it. And the bees that are on the outer edge, they're the ones that are unlucky, because the outer edge ones have to be against the cold air. So they experience the cold the worst. And so what happens is the bees on the edge are constantly trying to like burrow into the center of this ball of bees. And every time a bee goes in the middle, another bee gets exposed to the outside. And the bees keep sort of circulating in and out and in and out and in and out, because all the bees are trying to get away from the outside edge. And as a result, the best shape for that ball of bees is a sphere, because that means the smallest number of bees have to be exposed to the exterior. If you took that ball and made a long string of bees instead, way more bees are going to be exposed to the cold air, and therefore, you know, the bees are going to have a lower chance of survival. So water molecules individually are like those bees. They want to be surrounded by other water molecules. They want the most hydrogen bonds possible, and so they want to get away from the edges. So they form naturally these ball shapes. You see this too, like if you freshly wax your car and you go through a car wash, all the water will like beat up on these little balls. It doesn't like to spread out, because if the water spreads out, it creates a lot of surface, which breaks a lot of hydrogen bonds. It likes to form those little beads, those balls. All right, so hydrogen bonding, important in water. If you freeze water, hydrogen bonds sort of, they stop moving. They make this three-dimensional structure. We call this a crystal of water. And it kind of makes this hexagonal, you know, hexagonal shape. And it extends in 3 dimensions. So water, when it freezes, makes all of these hexagons. And we know that if you look at up close, if you looked at a snowflake, the actual snowflake itself has all these hexagonal features, right? You can see, like, obviously, it's a hexagon. This part, another hexagon. It's kind of like a fractal kind of thing, but there's hexagons all through this structure. And that's because if you go all the way down to the molecular level, the water molecules start out forming these crystals that are 3-dimensional hexagon shapes. So it kind of bugs me when it's like Christmas time and you see decorations all over the place with snowflakes. My office door has some on them right now still. Star Wars themed ones. Check them out, they're kind of cool. But it bugs me if there's snowflakes that people use as decorations that don't have 6 edges, if they're not hexagons. Sometimes you see 5, sometimes you see 4, sometimes you see like 7 or 8. If you have any of those in your house, just like break them and put them in the garbage, because from now on it's going to bug you too, because snowflakes are hexagonal. They have 6 sides, and it all comes down to the shape of the water molecule and how they optimize the maximum number of these hydrogen bonds when they form crystals. Great. Here's some, look. Does it make you want to cringe? 5. How many does that one even have? 8? I guess. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's not good. Don't do that. Water's not the only thing that can hydrogen bond. As I said, anything that has OH bonds in the molecule or NH bonds in the molecule can also do hydrogen bonding. And things that are hydrogen bonding, the molecules like to stick to each other. They also like to stick to other molecules like themselves. So they can hydrogen bond with other things that can also hydrogen bond. So often substances that are sticky are substances that have lots of ability to do hydrogen bonds. So here's a molecule of sucrose, sugar. If you took sucrose and you get it a little bit wet, and you, I remember like I had to do this for a lab once in biology where you take like a gummy bear and you get it a little bit wet and you rub it on your hands. And it was for some, I don't know, like you'd have to culture it or something. I forget what we did. Oh, I don't remember what we did. We had this like class of like 50 people, and everyone had to do this and get their hands all sticky. And then one person had like some kind of bacteria put on their hand. And then we had to do this thing where you had to go around and randomly find like 5 people and shake their hands. And then everybody at the end of the class had to like culture like whatever was on their hand. And you could tell, based on just that small number of handshakes, how quickly that bacteria spread to like everyone in the class, which is kind of cool. I don't remember if I got it or not. But anyway, you know if you were to do that, if you were to take like a candy, put it in your hand, it would get very sticky, very tacky, you know, your hands together like that. Things like syrup, molasses, these all contain sucrose, and sucrose is loaded with OHs all over the structure. OH, 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 OH. It's one molecule of sugar. So these will stick to each other, and they'll stick to water molecules too, because water molecules also have OH. That makes sugar stick to water really well, which means this is going to dissolve really well in water. So you can dissolve a lot of sugar into water. Molasses, this is just a weird aside. In 1919, there was the Boston molasses flood, where molasses was kind of the main way that sugar was transported. And it was brought into Boston typically from like southern areas, mostly like Brazil, Caribbean, places like that. And molasses was sort of like boiled down pressed sugarcane juice, and they would bring it up, and they would store it in these big tanks close to the harbor. And these tanks, they could take the molasses and they could refine it into white sugar. You could ferment it directly and make rum. And you know, there's lots of, you could use it directly, I guess, for a lot of different recipes and things like that. But there was a tank that ruptured. And that tank had, I don't know how many 1,000 million gallons of molasses in it. And it ended up killing 10 people. It just like this wave of molasses swept down from where this tank was. Basically like knocked down buildings. Like this is a picture of the site you can see right here. And it kind of washed out into the harbor. And apparently what happened, as soon as it happened, people like flocked to the area with buckets and like were taking a bucket of molasses so they could run home and get like free molasses. So I don't know if like what I would do if I had a bucket of free molasses, but I guess at the time, maybe this was harder to come by. If a molecule does not have any hydrogen bonding, there's a good chance it's going to be not water soluble. So here's some examples. Like this is a molecule of fat, like a typical fat you would find in meat or certain vegetables too, like coconut oil or things like that. And what you see here is there's lots of, the black circles are carbons, the white ones are hydrogens. So you can see a lot of CHs, but no OHs. There's some Os, but the Os are all bonded to carbons and not hydrogens. So no hydrogen bonding for fats and oils. And so when you mix fats and oils with water, they float to the top and don't mix. They don't dissolve. Waxes are similar. You know, there's lots of things that don't hydrogen bond, and they don't really dissolve in water very well. All right. So anything with OH, NH, FH technically too. FH, there's only a single molecule that has an FH bond, so I usually kind of ignore it. It's HF, which is a really nasty substance. If anyone here watched Breaking Bad, it's what they used in season 1 to dissolve some bodies. Fluoride is actually really bad. Like HF is bad because it sticks to calcium really well. It dissolves bones really well. So if you like spill it on your fingers, it'll start like dissolving your nails, and it can like sink in All right, my mic just died, so thanks for letting me know. I'm going to plug it in. Maybe it'll come back. Hopefully you can still hear me. Okay, I better turn this up. Okay, so now I'm using a little bit too much. Now I'm using just my iPad audio. This actually sounds usually pretty okay. You can tell me online if this sounds bad. If it sounds okay, let me know. But one thing, the reason why I like the wireless one is because if I'm standing in front of the computer, it'll pick my voice up. But if I like walk five meters that way, this won't pick me up at all. So if I want to do demos and stuff like that, the mic lets me travel wherever I want. I could talk from the top of the room and stuff like that. So hopefully this is all right. How long ago did my mic die? I don't even know. Anyway, we're good. What is the strong intermolecular force? So intermolecular means between two different molecules, or between two distinct, discrete molecules, not within a molecule. What is the strong intermolecular force that causes water molecules to stick together? That is called hydrogen bonding. Covalent is what holds the hydrogens together to the oxygens. But to get two molecules to stick to each other, that is hydrogen bonding. All right. So molecules that can do hydrogen bonding, molecules that have OHs and NHs, have a good chance of being water soluble. And here's some examples. We know sugar is water soluble. You can actually dissolve a ton of sugar in water. It's extremely soluble. Urea is another organic molecule. It's a waste byproduct from metabolism of proteins. It's found in our urine. And it has that structure there. You can see the NH2s on both sides. It has 2 NHs on each side for a total of 4 NHs. So urea can hydrogen bond like crazy, which is good because that means in our urine, it dissolves in our urine and just comes out as a liquid. Some things don't dissolve very well in urine, which is bad. If you get kidney stones, it's the result of certain things that don't dissolve very well in water. Is it calcium something? Kidney stones. Calcium phosphate, I don't know what it is. But anyway, it forms crystals in your kidneys, which can be very painful. Aspirin has an OH. It's kind of a biggish molecule with just one OH, so aspirin will dissolve a little bit in water, not as well as something like sucrose that has a ton of OHs, but enough. You know, if you take a pill of aspirin, it'll dissolve away in your stomach and you're good. Ethanol has an OH. Ethanol will dissolve in water. You can mix them in any proportion you want, and you're going to get them dissolving in each other. There's no limit to how much ethanol you can dissolve in water. Vodka is like basically a 40% solution of ethanol in water. Acetic acid is what you find in vinegar. Vinegar is like a 5% mixture of acetic acid in water, and it's got an OH, dissolves fine. This next one is melamine, and melamine is maybe not one you have heard of before. Maybe you have. It's got NH2, NH2, NH2. It can dissolve in water plenty well. Melamine is a bit notorious because this molecule contains a lot of nitrogens, which is good. I guess it's good. But there are tests that people sometimes do when they're testing foods, where they want to measure the amount of protein that's in the food. What they'll do is they'll measure how much nitrogen's in the food, because protein is really the only thing in food that contains any significant amount of nitrogen. There's no nitrogen in starch, in carbohydrates, and there's no nitrogen in fats, which are the other two major macronutrients you might find in water. Not in water, in food. So basically what they'll do is they'll take some food item and then they'll measure the amount of nitrogen in it and give it like a protein percentage based on the amount of nitrogen. And this might be something they might do for pet food or for baby formula or something like that, some product, some processed food. And what happened, there was a scandal, oh God, this is probably like 15 years ago now, where companies, not in North America, in other parts of the world were adding melamine to baby formula and to pet food. And the reason they were doing this is because when they sent it in for testing, the test came back and showed it had higher protein than it actually had, because it had all these nitrogens on this one molecule. So you can put one of these in and it says, oh, it looks like you have 10 times more protein than you really have. So they were able to kind of fudge the numbers for things like pet food, made it look more nutritious, and tragically baby formula. And a lot of this tainted food was given to animals. Turns out dogs are actually really sensitive to melamine, and like I think hundreds of dogs died as a result of consuming the food that was contaminated. And I think there was a lot of like babies that died too, like 30 or 40 babies. Not in North America, but other parts of the world. So melamine does dissolve in water, does have hydrogen bonding, and has a bit of a sordid history on its own. All right, other things we know dissolve in water that don't hydrogen bond, and a good example of this is salt. You know, we take table salt and we can put it in a pot of boiling spaghetti and it'll dissolve immediately. The way lots of ionic compounds or salts or metal containing, if you have a metal and a non-metal together, like sodium is considered a metal, what they do instead is they form these three-dimensional lattice structures, these crystals, with alternating positive and negative charged ions. And a lot of these will actually dissolve in water quite well too. All the different atoms here are held together by ionic bonds. And all an ionic bond is you have a positive next to a negative, and the positive and negative want to be close to each other, so they sit as close to each other as they touch. And this extends into 3 dimensions. And so if you actually like look at salt, like you take a box of salt, shake some out on the table, look at some of those salt crystals, little granules of salt under a microscope, they're like perfect little cubes. And they're perfect cubes because down at the molecular level, these form squares, right? And they form perfect cubes. Ionic bonds, so there's a picture of them. If you looked at, under a microscope, just salt, you can see all the like cubic little crystals like that. I remember when my kids were small, I bought them a container of Play-Doh once, and I opened this container up, and it had a bunch of like big cubes like that. Like they were probably like 4 or 5 millimeters on a side. And what I originally thought it was like shattered glass. Because if you take tempered glass and shatter it, it also forms little cubes that look the same. So I thought that like we're selling kids Play-Doh full of broken glass, which is, you know, probably not a very good idea. And I sent an email to the companies, like, what are you doing? And it turns out it was actually salt that was in the Play-Doh that had grown these big crystals inside the container. It like all come out of the Play-Doh. And I don't know what the conditions were, if it was like warm and cold or whatever during shipping to cause this to happen. But I confirmed it. This is what they suggested was going on. And I confirmed it by taking one out and dropping it in water, and it dissolved right away. So it was salt. Glass wouldn't dissolve like that. Still, it's a little bit weird. They sent us all this like free stuff, like all these like Play-Doh sets and all this kind of stuff. And I was like, no, I was just trying to make sure you didn't have like broken glass in that Play-Doh. But yeah, I should have done the test first. In your future, if you ever do that, open Play-Doh and there's white crystals in it, throw one in water first before you panic and think that it could be broken glass. Can't be just me. My brother, when we were like kids, we were at this restaurant and we had sundaes at the end, and he was like crunching his as he was eating it, and like mine was fine, everybody else's was fine, and he complained, he was like halfway through, and he complained like how his sundae was really icy, all this like ice that was in it that he was crunching. And it turns out it wasn't ice at all, it was broken glass. So he was eating a sundae that was like full of broken glass. And he was like, okay, he just, I don't know, worked through them, but like a little bit disconcerting, I guess. It was funny, like when I was a kid, I didn't think anything of it. Like, oh, whatever, you ate some glass, no big deal. But like looking backwards on that, it's like, yeah, that was kind of messed up. So what water does, because water has a positive end and a negative end, is you put this salt in water. If one of those positive ions, one of those sodiums, comes off the crystal, it gets surrounded by water molecules. And so each one of the negative ends of the water molecules will line up and surround the positive ion. And this is called solvation. It actually stabilizes the ions really well. The waters are happy because the negative ends like to be close to positive charges. And then the negative ions can do the same thing. They can line up with the positive ends of the water molecules. So this is why water actually dissolves things like salt really well, where a nonpolar liquid like an oil wouldn't dissolve salt at all. You might notice that too. Like sometimes I make like I roast potatoes, and what I'll do is I'll chop up the potatoes really small, pour in some oil, and then pour in a bunch of salt and mix it all together, then pour it out on a pan and then bake it. But the salt, like it's all grainy in there. Like it's fine after it's cooked, but it definitely does not dissolve in the oil. You can't like salt the oil the same way you could salt something that's liquid. You need something polar because you need the positive ends of the polar molecule to stabilize the negative charges, and the negative ends of the polar thing to stabilize the positive charges. And then this little thing will float around, and you have salt water. So what doesn't dissolve in water are things that are nonpolar, things that don't have hydrogen bonds, don't have OHs or NHs. And typically, if you have compounds that have ions where charges are like +2 or +3 or higher, they don't dissolve typically well in water either. And that would be the structure of almost every rock. And you know it doesn't dissolve in water because if you wade into a river, there's flowing water over these rocks, and the rocks will stay there for years and years and years. Slowly they'll break down through erosion, but that's a different process. It's not dissolving. All right, salad oil scandal. This is actually a very interesting story that happened, I don't know the year. It's in the notes, but I can't see the notes when I present something on here. Or can I? It's 1963. Someone told me. Okay, you can see the notes. Or you Googled it, one or the other. This is a swindle. It took advantage of the fact that oil doesn't dissolve in water. Basically, there was a company that would import salad oil, which is basically vegetable oil, canola oil or whatever. It would import it, store it in these big tanks, and then put it into bottles, distribute it. They were kind of like, they would take in the wholesale and then distribute it throughout the US. And at some point, they realized they could secure loans and use collateral. They could use all of the oil they had in storage as collateral for their loans. So what they did is they built a whole bunch of extra tanks, and they filled the tanks like 95% with water, and then they poured like a few feet of oil right on the top of the tanks and claimed, we've got these several million liters of salad oil. We want to take this loan out and use this as collateral. And an inspector from the bank might come along and open the top of the tank and look in. Sure enough, there's oil right to the top. They might even like take a little container and yeah, but they're not checking what's at the bottom of the tank. So they got all these crazy loans, and all these other companies, I don't know exactly all the details. There's a book on it right here. But all these other companies were somehow connected to this. And one company in particular that was connected heavily was American Express. And credit cards at this time were kind of a new invention. And they were sort of barely getting started. And American Express was heavily exposed to this. And eventually, like, the scandal got discovered. The value of this company basically went to zero immediately. And they had all these regulatory issues and all this problem. And it kind of tanked several other companies, and I think it caused like a noticeable blip in the stock market. And it caused American Express stock to go down to like half of their normal previous value, which was still very low because they were like a brand new company. It almost killed the company. And when it reached that bottom point, it was bought into heavily by one of the current richest men in the world. What's the guy's name? Not Bezos. No, not Elon Musk. They weren't even born yet. This is the 1960s. Not Bill Gates. I don't know where this guy is now. Top 5? His name's not coming to me right now. He's famous for, his company is Berkshire Hathaway. Berkshire Hathaway, which is a big investment company. Yeah, Warren Buffett. That's right. Yeah, Warren Buffett's this guy's name. He was like number 2. Like a couple of years ago, he was like the number 2 richest man in the world. Bezos and Elon Musk passed him. He was always sort of like number 1 or number 2 with Bill Gates for many years. And what he did is he like, so I'm getting Buffett in the chat now. What he did was he invested heavily in American Express shortly after the scandal. And then American Express like rebounded and then grew into the company it is today. And he was there for the whole trip. And I think something like for Warren Buffett's fortune right now, which is I don't know how many billion, some like significant fraction of it was because of American Express. I don't know what the number is, like 18% of his money is in American Express or something like that, but super rich now. So keep your eyes open. If you see an opportunity like that, new technology that just gets tanked, well, I don't know. That could be bad advice 99 times out of 100 too. He got lucky. Which of the following compounds below should be most soluble in water? What are we looking for? We're looking for molecules that have an OH or an NH somewhere in the structure. No oxygen or nitrogen, no oxygen or nitrogen, no oxygen or nitrogen. That's got 2 NH bonds. It's got NH2 at the top. So this we expect to have hydrogen bonding. This we expect to dissolve in water. That molecule is called aniline, if anyone cares. Now, one issue with water that comes into your home, depending on where you live, depending on if you're on city water or on a well, is something called water hardness. And water hardness refers to the amount of calcium and magnesium ions that are present in the water, present dissolved in your water. So the problem is that calcium and magnesium ions can react with certain things that you could mix in water. And also, if you heat that water, and it's hard water, it can lead to insoluble solids depositing out from the water. So you can see that here. If you take water and heat it in a kettle and you have hard water, what will happen over time is solid, insoluble calcium carbonate will form from the calcium in the water and carbon dioxide in the air. Heating it will cause it to come out as a solid, and you see this cut open kettle has all this flaky white solid in there. Now it turns out calcium carbonate is very soluble in acid. So if you actually like pour vinegar into this and swirl it around in there, it'll dissolve it all away and fix your hard water issue. I noticed this inside my dishwasher. If you spray hot water inside your dishwasher, you can get hard water buildup inside your dishwasher, which can lead this white powdery stuff to deposit on your dishes or deposit on the inside. The trick is add vinegar or add citric acid or some acid to dissolve that buildup. This is inside a hot water pipe, and you can see how this could become problematic if you suddenly have so much buildup that you don't have any flow anymore. I'll tell you where I find water hardness is important too, is inside irons. Because if you use an iron to, flatten out your clothes, you got to put water in it to create the steam. And of course, you're heating the water to make steam. And when it makes the steam, it has all these like very fine holes that the steam comes out of. And very easily, your whole, there goes my, very quickly you can have your kettle blocked up with hard water build up inside. So the trick is, if you get yourself an iron, get yourself one and use distilled water in it. You can buy distilled water in the store. Distilled water doesn't have any calcium or magnesium. This is one of the best purchases you can make in your life. Go out and get a good iron. Not like a crappy $25 iron. Spend like $100 and get an iron that's going to last you forever. I tell you, I had a crappy one for many years, and I got a good one, and it was like, whoosh, and it's done. And like before, he'd be like, back and forth, ironing my clothing. And it was like, none of this. Get a good one, put distilled water in it, and you're good. If you have one that you've already blocked up with hard water, maybe, I wouldn't use this on anything good, but maybe you could like pour vinegar in it, and that's probably a bad idea. It might vinegar has a problem with rubber seals, which is why I use citric acid. Citric acid would be bad in an iron because the citric acid would form crystals and stuff inside too. That's why vinegar is good. Just chuck it out and get a good one and use distilled water. Life lesson. The other thing calcium and magnesium will do in hard water is react with soap. Soap is a big long molecule like this. It comes from fat. Take fat molecules and hydrolyze them, treat them with base. You get these soap molecules. And what the soap molecules will do is react with calcium or magnesium to make solid material. And this is usually like white, powdery, a little bit waxy kind of material. And you often see this build up places where water and soap might come together, namely your bathtub. So if you're someone that takes baths a lot and your water is hard and you use like regular bar soap, what you'll notice over time is like a ring build around the tub. And that ring is not something you can just wipe off. Like you can't, it's really difficult to get rid of it. And that's hard water. Sometimes we call it soap scum. And the soap scum is just this buildup of this insoluble solid between the hard water ions, calcium or magnesium, with the soap molecules itself. You can get rid of it though. You can scrape it off, one thing, or vinegar. Acids will also dissolve soap scum. So if you see it build up, go at it with that. Okay, that's the way to fix that. Vinegar will always work. I used to wonder as a kid, it just seemed inefficient to me. Like I used to use bar soap when I was a little kid, and I'd use shampoo for my hair. And I was like, they're both like cleaning. Why can't you just use one? Why do you need a separate thing for your body and then something different for your hair? And the reason for that is actually because soap will form soap scum, and soap scum likes to stick to things, and one thing it loves to stick to is hair. So if you use bar soap to wash your hair, your hair would get really like waxy and like limp and dull looking. And people realize this right away and develop shampoo, which is not the same soap. It's a detergent. It's usually a sulfate like sodium dodecyl sulfate or sodium lauryl sulfate. And that does not form deposits on your hair. So people had a separate thing for your hair to prevent the soap scum problem. And they thought, soap's good for the rest of you, that's okay. But for your hair, you need something different. Now you get body wash. A lot of people just use body wash, which is basically just shampoo. And you use shampoo for your whole body. I think the reason why people use two different things for a long time was because bar soap was just a lot cheaper. So you could use the expensive stuff for your hair where it's needed and the cheap stuff for the rest of your body. Now, probably either people don't care so much about the price difference or the shampoo is just as cheap as the other stuff, so it doesn't matter. Either way, don't use soap for your hair. Or if you're like super hairy on the rest of your body, bar soap may be a bad idea too. If you want to be soft and velvety, where, use body wash. I always find it funny though, like when I buy, I like 2-in-1 or 3-in-1. I just like one thing. I don't have to think about lots of different bottles. I'm alone in my house. There's lots of different bottles that are not mine in my house. But I saw one and it was like a 4-in-1, and it was like shampoo, conditioner, body wash, and body conditioner. I'm like, what's a body? I didn't know what body conditioner was. But that was beaten. I saw it was like an 8-in-1. But the 8-in-1, like 4 of them were just 100% bullshit things. It was like, it moisturizes, it conditions, it brightens, it like, I don't know. It was all these words that didn't have any meaning behind them. Like you couldn't actually, anyway. I'm a little, with like the whole cosmetics and beauty industry, I'm very like, a lot of the advertising to me is advertising things that aren't real. Also, the other thing you see a lot in shampoos is they'll just add random stuff to the shampoo to make it sound like it's better, but that does absolutely nothing. Like shampoo with vitamin E. And it's like, if you had any idea what vitamin E is and how it works, putting it in your hair can't possibly do anything. The other one is charcoal. I see a lot now. They'll add charcoal to everything. It's like, I know we're going to talk about charcoal later in this chapter. It's not going to do anything in your shampoo. Okay? It kind of looks cool though. It's like makes your shampoo black, but I don't know. There we go, soap scum. One problem with soap scum is in your washing machine. So that's where you put hot water, and that's where you put detergent to clean your clothing. They can react in your washing machine and make soap scum, and that soap scum can deposit out on your clothes and kind of leave like a white powdery residue on your clothes, which people don't like. It also destroys some of the soap. Basically, it inactivates some of your soap that you've added, so it doesn't do a good job cleaning your clothes either. So the industry came up with a solution, which was to add a substance called sodium tripolyphosphate, STPP, to laundry detergent. And what STPP does is it seeks and destroys calcium and magnesium ions in water. It has this kind of a structure. It's got 3 phosphorus, 10 oxygens, a charge of -5. It basically goes around in the water, and if it finds a calcium or magnesium, which I'm going to abbreviate here as M, as a metal, it basically wraps around it and prevents it from doing anything. So basically it allows the soap just to be soap and not have any magnesium or calcium to deal with. Kind of just goes and cleans the water of those 2 particular ions. Joey says 9-in-1. Shampoo, conditioner, motor oil, body wash, detergent, gasoline, sports drink, lighter fluid, cooking oil. Yeah. So STPP, great. It gets rid of that problem, and it boosts the strength or cleaning ability of detergents and prevents that buildup of like white crud that can happen in your washing machine. The only problem is that if when you drain your washing machine and this all goes down the drain and ultimately into lakes and rivers or whatever, phosphate is a fantastic fertilizer. And so when it gets into water, it causes algae to like take off and bloom. And it causes your lakes and rivers to turn green like this, which is bad because algae will grow very rapidly. It will then die equally as rapidly. And when it dies, it decomposes. And when it decomposes, it uses up all the oxygen in the water. And when it does that, the fish have nothing to breathe, and the fish all die and float to the surface. So it can be very disruptive and damaging to natural systems to be dumping large amounts of phosphate in there. Same thing as if you have agricultural fertilizers that you're dumping into rivers and lakes and so on too. Same thing as if it's coming out of your house. So for a lot of years, for environmental reasons, they took it out, and most detergents were advertised as being phosphate-free. And I'm not sure what they used to fix the problem. Let's see, it says friendly to lakes and streams before I covered part of it up there. So phosphate-free became a big thing. Then it kind of faded away. I never see things advertised anymore as phosphate-free, but for a while it was kind of important. So this hard water can be a real issue in lots of different situations. And there's lots of ways of fighting it, I guess. Another way of fighting hard water is to get a water softener. And I don't know, does anyone here have a water softener where they live? You often see it at cottages, and mainly in cottages because cottages are usually more remote and not really connected to town water. Water softeners have two parts. They have what's called a brine tank, which is a tank full of salt, and they have basically the main tank in there. And the way these work is they have little beads. We call it often an ion exchange resin. They're like plastic beads, and what it says iron exchange, it's ion exchange. And what happens is they're like studded, they're covered in sodiums. All this material is covered in sodium ions all the way through. And what happens is when you take your hard water and you flow it across these beads, flow it through, what happens is the magnesium, which is 2+, and the calcium, which is 2+, is doubly attracted to the resin compared to sodium, because sodium is only +1. So what happens is that the calcium and magnesium stick very strongly to these little beads, and when they stick, they displace sodium ions. So when you come out the other end, the magnesium and calcium all has been sort of scavenged by the resin and replaced for each instance with 2 sodiums. So it increases the amount of sodium, decreases the amount of magnesium and calcium. This only works for so long, and then you've saturated all of your ion exchange resin. It can't capture any more calcium or magnesium. So then what you have to do is run a second cycle. And these are often timed to run it like in the night or something like that. And then what happens is you get these bags of salt. They come in these like bricks, little bricks of salt. And basically what you do is you force salt water in reverse, super concentrated salt water, backwards. And what that does is it basically, just by brute force, there's so much sodium, it knocks off all the calcium and magnesiums in reverse, and it cleans it, dumps them somewhere, like down the drain, and then it replenishes all those beads so they're all covered with sodium again. So then you can run it in the normal direction and capture more calcium and magnesium and have nice soft water come out the other side. So of course, to do that, it consumes salt, consumes a lot of salt to like recondition the column to get it back to where it was before. Yeah, water softeners are a good way to go. This is the tank, of course, where you put the salt. This would be the tank where the ion exchange resin is. And so, yeah, it runs in cycles back and forth, usually on a timer, Question 8.5. Hard water comes from the reaction of carbonate ions with what metal ions? Magnesium and K+. What's K+? That's potassium, yeah. It's one of those weird ones where like the symbol doesn't match the English word for it. But that's okay. There's a couple like that. Iron's another one, which is Fe. Tin is Sn. What else? Antimony is Sb. Sodium, yeah, sodium is Na. Gold is Au. Silver is Ag. That's right. What's that? Lead is Pb. That's right. A bunch of them. But they make sense if you look at other languages. Like lead, I think Latin is plumbum for lead, where Pb comes from. Same, like iron is like, what is it in French? Fer, fair. But it's not based on French. It's based on the Latin, which is where the French is based. Anyway, we're not going to get into that. The answer is magnesium and calcium, and they're both 2+, not C. C is magnesium and calcium, but they're the wrong charges. So it's important that they're 2+, because they have such a high charge, that's why they stick to things so well, and things like sodium does not. Cool. That's what that crust is on your hot water tap. How do you clean it? Vinegar, yes. Or better yet, citric acid. Everyone should have like a 5-pound bag of citric acid in their house. What's the purpose of adding TPP or STPP, sodium? It's to complex the calcium and magnesium ions. In the case of laundry soap, it's to prevent soap scum. So it would be D. We're doing great. 207. Well, the next whole unit that we're going to be talking about, second half of this, is going to be talking about drinking water, safe drinking water, how we make it safe if it's not safe, how we regulate it, things that we put in water, things like that. And I'd like to start out with this map of the world, which is showing in different regions of the world the percentage of the population in these places that have regular access to safe drinking water as a fraction of total population. And we're lucky to live in a country where most people have that. Yeah. And how, what, sorry? Right, so yeah, the question was for people online, is there a relationship between access to safe drinking water and the degree of development of the country? Or like GDP, you could say. And absolutely yes, absolutely. For most developed nations, high GDP nations like Canada, safe drinking water is largely like a forgotten problem. You see certain times it flares up. Certainly in Canada too, there's a huge issue right now with certain First Nations groups and access to safe water. You've seen some recent ones maybe in the US, like in Flint, Michigan a couple of years ago. There was a big issue. So it's not like there are no issues. But for most of us, we don't have to think. We just turn the tap water on. We don't think about what's coming out. We just assume it's safe. We just assume that our day-to-day lives is not at all really dominated by figuring out how we're going to get our drinking water to be safe. Every once in a while, there might be like a boil order or something, and you got to boil your water before you use it for food. Or you may be at a cottage where the E. coli counts are such that you shouldn't be drinking it or whatever. But, many parts of the world, it's a severe, major challenge. It's one of the major causes of diseases worldwide. Lack of access to safe drinking water. So definitely strongly correlated with how well off a country is. Yes?
But the hardness of the water doesn't impact like it's healthy or not. I know from the body perspective, hard water doesn't taste really healthy, but it's not unsafe to drink.
That's right. So one of the questions was the safety of water as a function of like whether it's a hard water or not. And hard water can, you're right, affect the taste a lot. And but it's true, it doesn't make it unsafe. Calcium or magnesium are actually required nutrients for our bodies. Like we get most of our calcium and magnesium from our diets. But drinking water with calcium and magnesium is actually arguably good for us. Probably makes no real difference if we have a healthy diet anyway. But it certainly doesn't cause us any harm. So like the presence of those ions in waters don't constitute like a safety thing for us. But yeah, you mentioned coffee and how coffee tastes if you use hard water versus soft water. What I notice too is carbonated water. I go through like a phase every summer where I drink a lot of carbonated water. And if you use like one of those soda streams, I find like tap water makes really gross soda stream water. But if you run it through a Brita filter first, which is similar, we'll talk about those later, it like makes it way better. Part of that is maybe water hardness. Part of it may be chlorine that could be in tap water too. We'll talk about chlorine in water as well. Yes, they have. Carbon doesn't take calcium. Carbon in Brita filters will take out the chlorine. It also has ion exchange resin as well, and that is what will take out the calcium and lead and cadmium, other heavy metals like that. Yeah, we have a whole thing actually later in this unit on what Brita filters do. Yes.
So my mom has like well water, and sometimes it smells like metal and tastes like metal, and like sometimes it stains like your toilets and like the shower. What is that?
Yes. And it's brown, right?
Yeah.
Yeah. So that question was for people online. Um, when you are on well water and you get water that has a metallic taste, and sometimes it's colored and it can like stain toilets and stain, other things like that. Like even it can even stain things like a teapot, or whatever.
It stains like when we wash our like sheets, it stains the sheets when we wash it.
Right. So it's usually brown in color, and usually what that is iron in the water. And iron is just again one of those things that depending on what the geology is of your area where you drill the well, there can be iron in your water. It's basically like rusty water. It's effectively what it is. And again, iron can affect the taste of water, but it has no health implications. Iron, again, is another element we need to consume. We get it from things like red meat, or lots of different vegetables have it, and it's a required nutrient for us to make more hemoglobin. So it's not a danger per se, but it is kind of stubborn, right? Um, Iron, I think, would probably be removed by water softener, because iron ions are 3 plus, so they should stick really well to the resin. The other way to get rid of it, and this is what my brother does, because he has a well, and he has very rusty water, where he is a reverse osmosis system, and we're going to talk about that again later on in this way too. There's a way of cleaning that out of water. Oh, cool. Yeah, reverse osmosis. So that should work really well. The problem with reverse osmosis is you end up wasting a lot of water. So if your well doesn't produce a lot of water, and you throw half of it out because of the RO system, you may like be short on water different times a year depending on different things. But yeah. Ryan Hutchinson says, "What's the issue with the gym's tap water?" That's an interesting one. So I think what the issue is with a lot of water on campus is lead. And lead is toxic. Again, dose makes the poison and blah, 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 blah. But lead is not naturally found in the water, but it's often found in buildings where the plumbing is old, because they use lead solder to solder pipes together. They've done that for many, many years, going back to Roman times. And the issue is not when you have flowing water that flows a lot. It's when you have water that sits stagnant for a long time. So if you're in an old home, this is likely going to be the case as well. If you like leave for 6 months and come back, turn on the taps, there's probably going to be a lot of lead in the water. So all the taps at Acadia are sort of constantly monitored a couple of times a year. Basically, someone turns on the tap, takes a few milliliters, and actually in the chemistry department, we have a lab called the Acadia Lab for Agri-Food and Beverage, and we actually do some of our own testing on the tap water that we drink. And we know what the allowable limits are and so on. And it's true, if you turn the tap on and take a little drink of water, the lead levels can be over the limit, but if you leave the water run for like 5 minutes and then do it, it's good. It's almost like you got to clean the water out that's been sitting in the pipes, and then it's fine. So in the gym, other parts of campus, probably residents, if the water is being used all the time and it's constantly flowing, it hasn't sat in the pipes long enough to pick up any appreciable amount. And that's why like individual taps are often labeled, this is not safe to drink, this is, this isn't, this is, this isn't. And it has to do probably with how frequently that tap gets used. Because if it gets used all the time, it's probably safe. Now I'd expect in the gym, like I know in the fitness room, they have like a filtered system. That should get rid of the lead. So I think that water in there would be fine. Or anytime like where you have like bottle filling stations, that's always filtered. But if you, I don't know what it's like in residence. I would think there'd be so much water moving that that wouldn't be an issue there either. But it does just run it for a while and then, yeah. So that's why. That's in there because of the old buildings, old pipes. The same would be true of any building that's more than 30 or 40 years old, probably. They really moved away from copper piping, like metal piping. Most modern builds, like anything since 2000, probably has like PEX, which is cross-linked polyethylene, which is plastic flexible tubing for indoor water, hot and cold. And older buildings all use typically copper, which is more expensive. And it has other negatives too, like this lead solder that people used for a long time. So yeah, the tap water, it's not going to kill you either. It's just one of those things. If all the water you drank was lead contaminated, you have a higher risk of a lifetime outcome of some negative health thing. It's not like you drink it once and you're going to die or anything like that. It's a chronic effect having that water in there. Yeah, so that's good. We only have a minute or two left. I just wanted to say that we do a lot of things to our water to make sure it's safe when it comes out of the tap. And we're going to discuss some of those in detail in this course and what we actually do. This was actually, in 2010, there was an earthquake in Haiti, very devastating earthquake. And the Red Cross went and handed out drinking water because a lot of infrastructure was destroyed and so on. So they had these like little bags like this of drinking water that were being provided to people, of course, for free and make sure people had something to drink. And it says right on it, it's in French, but that says purified water, reverse osmosis, which we're going to talk about, ozone, which we kind of talked about before, but we'll talk about briefly again, ultraviolet, we've seen that before, ultraviolet light, and that's in particular how this water was purified and disinfected. And we're going to look at, different methods that we use to make sure our water, first of all, doesn't have any like dissolved substances in it that could be dangerous, and second of all, anything living in it that could infect us with disease or something like that. This is where I'm going to leave it today, though. We're going to come back to this topic on Thursday, I guess. Cool. Awesome. So see everybody online next week as well.